Hey Algebra 2 Honor students, I wanted to do a couple quick examples just to add on to what we got to say in class. Class was a little shortened, didn't quite get to say enough. So here are a few examples to cover 6.2, rationalizing the denominator. We'll do basic and then we'll do something that's a little bit more advanced. Okay, so first, when you are rationalizing the denominator with squares, the key is we want to get the denominator to be rational. And when you have square roots, it's quite easy. The trick is multiply top and bottom by the square root that you see in the bottom. Although I just noticed that actually on this example, we could simplify first. So this would be 4 square root of 3. And then 4 is a factor of 12. So this would be 4 times 3. That 4 can come out of the square root. So 2 root 3. And then in this case, it turns out we don't need to rationalize the denominator because the square roots of 3 cancel. And I'm left with this divided by this. 4 divided by 2 is 2. And this is a case where just by simplifying the square root as is, they canceled, and so we didn't need to rationalize. Now, if you rationalized, if you said, oh, I noticed this, I'm going to rationalize the denominator, then you might go, oh, I'll just do square root of 12, square root of 12 in the top. So we multiply top and bottom by square root of 12. We get 4 times square root of, I'll just put 12 times 3 under here. Down on the bottom, I would have the square root of 12 times the square root of 12, which is 12. 4 divided by 12 reduces, so I would end up with a 3 in the denominator. In the numerator, I have the square root of, let's see, well, 12 times 3 is 36. And square root of 36 is 6. And 6 divided by 3 is 2. So if you rationalize the denominator first and then reduce, you'll get the same answer. But what if I changed the problem? So what if this was 4 square root of 3 over the square root of 5? Okay, now multiply top and bottom by the square root that's in the denominator. And I get 4 square root of 15. Square root of 5 times square root of 5 is 5. And there's really nothing else I can do because 4 over 5 doesn't reduce. 15 has no perfect squares that are factors. And we have rationalized the denominator. Okay, what do we do when we have cube roots? Okay, so first thing is well, if you think about your perfect cubes, 1, 2 cubed is 8, 3 cubed is 27. If I start going through with like 4 cubed is 64, 5 cubed is 125, etc. None of these are factors of 175 or 50, but I do notice that this is the cube root of 175 over 50. So this is one of the properties in this section. If you have the cube root of the numerator divided by the cube root of the denominator, you can put the cube root over the whole fraction. And this fraction does reduce. This is the cube root of, 25 goes into 52 times, and 25 goes into 175 for 5, 6, 7 times. So this would be 7 over 2. Now I can resplit them. Cube root of 7 over cube root of 2. And now I've got that as reduced as possible. I want to rationalize the denominator. Easiest way to do this when you have a cube root is I need to write a cube root, and I'm going to write a cube root up here. I'm going to multiply top and bottom by the same thing. And I want to multiply the denominator by something that gets rid of the cube roots. Well, 2 squared is what I want under here. Now here's why. I want to multiply by something so that when I multiply this by this, I get a 2 cubed underneath. So I end up with I end up with the cube root of 2 cubed. Then the cube and the cube root will cancel each other out. So whatever you write on the bottom, you write the same thing on the top. And so in the numerator, I have the cube root of 7 times 4, 28. And in the bottom, I have cube root of 2 cubed, cube root of 28. Sorry, that was a little bit too big there. Cube root of 28 over 2. And we have rewritten the original situation in its most simplified form. Okay, use a few different radical properties there. Last one. Simplify and rationalize the denominator. Also, the instruction you will see in the book is it will say, assume all radicals represent real numbers. I'm going to emphasize this in our upcoming lessons. Assume this represents real numbers. Okay, well, what does that mean? Well, can you see that? Let me just pick purple here for a second. A little side note. Can you see that y actually needs to be positive or 0? It can't be negative. Why is that? Well, what if y were negative 2? If y were negative 2, then negative 2 to the 5th would be negative. And then the 4th root of that would be not real. In other words, this y to the 5th could be negative if we allowed y to be negative. And if we allowed y to be negative, y to the 5th would be negative. And the 4th root of that would be an undefined operation at this point because we're only dealing with real numbers. So we know just from the setup of this, by doing a little analysis of the domain, we know that, let's just write this down. We know that y must be greater than or equal to 0. What about x? Same thing. Notice that x is to the 9th power. If the 4th root of x to the 9th is a real number, then the x's we put in here cannot be negative. Because if I put a negative in for x, negative number to the 9th power is negative. The 4th root of that would be the 4th root of a negative, which is not a real number. So we also know that x must be greater than or equal to 0. Hence, we don't have to worry about absolute value on these problems. When we first started learning the rules, I didn't really emphasize this because I wanted you to kind of drill into your brain that an even root to an even power is going to give you an absolute value when the variable comes out. However, if you do a full analysis of the domain before you start, you may find that actually there's no way for the variables to be negative at all, like in this case. So I actually don't need to worry about absolute value at all. Let's do the problem now that we know that x and y cannot be negative. So this is 4th root of x to the 8th, y to the 4th times an x. So I rearranged things and I pulled off one factor of x here. I want the powers that come out to be multiples of 4. In the denominator, I have a 4th root of y to the 4th times another y. So we get x squared y times the 4th root of x. And in the denominator, 4th root of y to the 4th is y. Now, normally we would have to be careful about absolute value, but we know that y cannot be negative in this case. 4th root of y. Okay. Y's cancel. And I'm left with x squared fourth root of x over fourth root of y. Now, I want to rationalize the denominator now. All right. There was another way to do this whole problem, by the way. I'm just doing it this way to kind of emphasize some points. Okay. Now, I have x squared. Actually, you know what I'm going to do? I'm going to erase this, and I'm just going to multiply right now by what I should multiply by. Fourth root of. Now, how many factors of y would I want in here to make sure that y times this becomes y to the fourth? I need 3 factors of y. So I'm going to put the same thing up on top. All right, and I'm almost done. X to the fourth, x squared. I'm going to put x squared, that's my exponent. And now when I write the radical, when I handwrite the radical, it's good to put a little notch here on the left, and then put your index of your radical in there, nice and tight, so that it's really clear when you write it. And in here, we'll have x, y cubed over. And then the in the bottom, we're going to have fourth root of y to the fourth. And maybe you can start skipping a step here, but this would be x squared. And then the fourth root of x, y to the third over y. And that is our simplified, most simplified version that has a rationalized denominator. All right, I will see you in class.